Hello, everybody. We're here today to talk about failure and embracing failure and how actually it will help us build better and more resilient applications if we do. Failure is inevitable. We all know this. We all work with computers. We all know that your computer can crash. You join that Teams call on a Monday morning and Teams decides it's not going to work that day. We all know in building software that sometimes bugs happen and that has an impact on end customers. So we're not here to try and avoid failure, but just really to talk about what can we do to minimize its impact as much as possible when we're writing code. So this is me, I'm Callum. I'm based in Sydney, originally from the UK, moved here a couple of years back. This is my second DDD Melbourne, so it's a real privilege to be back speaking with you all today. I'm a Microsoft MVP of 6 years. I also work with a .NET-based CMS called Umbraco that is fantastic, and they're sponsoring today. They've got a booth downstairs. Go play, go do their challenge. I've cheated to get my way to the top of their leaderboard, but it's a good fun challenge. Go have a go. By trade, I'm a .NET developer, and so today I'm going to show you some examples in .NET, but also JavaScript. And if you're not a .NET developer or a JavaScript developer, don't worry, because there's also a lot of conceptual stuff too that actually applies widely across the board in basically any programming language or any tech stack that you want to work in. So that's that. I go by the Chief Bumpster. I run a consultancy called Bump, and to avoid recruiters finding me on LinkedIn, I chose that as my title. So this is me. You can reach me on various social medias there. I'd love to catch up after. I'm around for the rest of the day. So failure has been particularly prevalent in some of the work that we've been doing actually in the last 3 to 6 months, let's say. Back in November the 18th to be precise, Cloudflare decided to absolutely crap its pants, to be very blunt. What happened here? I'm sure many people in the room use Cloudflare on a regular basis. You put this in front of your production systems. It's something that carries a huge percentage of the internet's traffic. We're sort of talking like 20-25% of the internet's traffic runs through Cloudflare. And so when Cloudflare had an outage, it took down about 25% of the internet with it, which is a really scary thing. It revealed to a lot of companies that they've got this dependency on a provider that probably they don't even pay money to, or even that much money to, that is integral to their customers being able to access their web services. That's quite a scary thing. And Cloudflare does take this with great responsibility. They have really great technical in-depth write-up of what happened with this issue. Essentially, they have a bot management platform, and that bot management platform's job is to detect patterns that bots perform against websites to prevent them from accessing those sites. And they have a big rule set, and they deployed an update to that rule set that took the length of the file that contained those rules over a certain limit where the untrusted code they were running in Rust suddenly went, nope, I'm actually not going to open that amount of data anymore, and failed. Widespread. Every single Cloudflare site was down for around 30 minutes. But it felt like hours, because the cascading effect of this was huge. You had other systems that maybe took longer to get back up online and to recover. Cloudflare itself is a globally distributed network, so whilst they had fixed and isolated the issue within 30 minutes, it takes many hours for those fixes to propagate and for customers to start feeling happy and comfortable again. And then about 2 weeks later, another incident happened with Cloudflare too. This is just one example of failure at large scale. Another is this, and it's a fantastic image because it depicts so many things personal to me, but also things that we experience on a daily basis. Anyone that uses Windows is familiar with this blue screen of death. But back in 2022, Windows customers experienced a different issue, where most large corporations in the world were installing a kernel-level virus manager security tool called CrowdStrike, and an update was applied that bricked upwards of 1 billion Windows machines globally. How crazy. And imagine if you were working on that scale. I really feel for the person who feels responsible for pushing that. It certainly wasn't their fault. But this then ensued days, maybe weeks, of companies having to go out and manually patch some of these bricked machines to remove the CrowdStrike bug, revert the version back. Some people got lucky, some people were using a different product, or some people just didn't have that update apply in time before it got pulled. But the net result of this was airports, hospitals, Really critical infrastructure, rail infrastructure, shutting down. They couldn't run their computer systems. For me, working in applications, we had APIs that were running on services where they were also running CrowdStrike software. And they either had massively reduced capacity as a result, or their API was simply offline for many days. This actually highlighted to us where we were heavily dependent on some of these services, and just because some other system goes down that we maybe don't directly depend on, why is it affecting our application? We'll talk a bit about that in a minute. Another one, and I love to use this example, weather happens, we all know that, and especially this sort of time of year in Melbourne and Sydney where I'm based, we get some nice big electrical storms, and that's all good fun. For some reason, and I'm sure somebody in the room is smart enough to know the exact reason why, I don't, big cloud vendors like Amazon, like Microsoft, Cloudflare as well, have decided that they have this global network, but they do have a primary data center. So they'll have a single data center that is effectively the mother data center. And when they need to spin up a new data center, it's effectively cloned out of that. In the case of Microsoft, that's actually in the US. It's in the east coast, the southeast coast of the US, and they get a lot of storms. And Microsoft built a product called Entra ID, formerly Azure Active Directory, and this is an identity product central to the way that identity and authorization works across basically their entire infrastructure. And it turns out that doing identity at scale, and especially at Microsoft scale, is quite tough, and that identity product was heavily reliant on this one data center being online. So in 2021, it got taken out by an electrical storm, perfectly understandable, it happens, but with it they took a cascading, rippling effect across many other services in Azure and in consumer products that you'd be using as well. Huge issue. Of course, Microsoft's done some things since. They've produced a great post-mortem that explains how they've been trying to globalize this fairly archaic service and make that work in a distributed fashion where it's not reliant on one region. It highlighted all of the areas where actually different people's applications or different services in Azure were dependent on this region, and they could maybe try and decouple it. But it was an interesting lesson for us. The point I'm trying to make here is failure is common. It happens to the best of us, Microsoft, Cloudflare, and, well, basically the entire world in the case of CrowdStrike. But there's, very well publicized AWS outages. There was even a Cloudflare outage this morning, so it happens. We can't do anything about it. We just have to try and work around it. So typically we build, in my company, sort of web applications and APIs that we use .NET and we use Azure, but other infrastructures and languages are available. Probably many of you in the room do a similar thing, and you build an application that's hosted on a server, maybe a PaaS product, and you're hosting things like line of business applications that might go and talk to other systems. The chances are you've got a server somewhere that's talking to another API that's not in your control, to a third-party vendor's API. You possibly also have a system that's sending out emails. So whilst that, unlike with the API, might be a two-way thing, you might be receiving data from the API and you might be posting data to an API. Email is a bit more transactional. You open a connection, you say, hey, email server, please send this thing to this customer. You might have integrations like CRM and things that ensure that your customers can see their orders in their account. And you might have something a bit more complicated, like payments. And this is a really high-level look at what someone's overall typical application might look like. And you can start to see where we're dependent on so many different parts of a system that you probably wouldn't realize you are. And it's an interesting time to question, well, what happens if one of these becomes unavailable? There's other bits of your infrastructure too that often we don't consider within the same vein as an API, our database, our storage, monitoring tools. In cloud platforms like AWS and Azure, databases and storage are going over a network. That is not a process running on the same box, most likely, as where your web application might be running. So there can be latency within a data center that then affects your connection to the database or your storage. If you're relying on low latency connections to anything in the cloud, the chances are at some point it's going to fail and it's going to affect your application. The more advanced users in the room might have something that looks a bit more like this, a more distributed architecture. This is essentially the same thing I just showed you. Think of it as an e-commerce business where we've got microservices, and each of those services is independent from your overall application. Your front end here talks through a gateway and talks back to these different services and these different backends. But ultimately, you're just moving the problem. It's a big ball of mud being split up into lots of little balls of mud. We have a catalog service in this case that talks to a database. It has its own database. We have a checkout process that's job is to collect customer data and then handle the commercials of the transaction. Again, it has its own database. If you're running an e-commerce business, you'll have an inventory service that's responsible for managing your warehousing tool and another database. And then you'll need payments. And the payment service job might be to collect payment, connect to the Stripe API or PayPal or whatever we're using nowadays, and then send an email to the customer saying, thanks, we've received your order. There's so many different dependencies within this system that it's quite difficult to model what happens if one of those things goes down. We typically think of downtime and reliability as the entire system, but in this case, maybe not. We need to define actually what healthy means in this case. How are you measuring your application health? How do you determine that we have an incident and there's something we need to go and do about it? Probably the majority of people, and especially those in here that may be building web applications, would use a tool like Pingdom or Uptime Robot. They're these fantastic tools that poll your application from different endpoints globally and tell you if it got a response that was not a 200 OK. And that's great, but it doesn't actually monitor your overall application health. If the application is just slower because you're dependent on a third-party API, maybe that matters to you as a business, and that's maybe something that you want to think about trying to handle or isolate. Or maybe it doesn't, and that's okay. We don't have to over-engineer our applications around this, but in the majority of cases, you don't want a third party to take down your website homepage or your one of your API endpoints if you can avoid it. Quite a good metric that we can use to define health is requests per second. How many requests is your service actually able to handle on a regular basis? But this is so subjective, and it's quite difficult to measure because requests per second could differ, annually based on Black Friday. An e-commerce store is going to get far more traffic versus on, New Year's Day when everyone's a bit hungover at home. Request performance is actually a more interesting one. So of the number of requests that we're receiving, let's take the 95th percentile of those requests. Are they within a tolerable threshold for us? That's actually a really good way of measuring your application's health because it's not subjective based on the amount of traffic you're receiving. It's just based on end user experience. How fast is our system able to respond to a customer request? But again, this is also flawed, and especially in cases where you depend on multiple different APIs or multiple different third-party services. And when we're talking about health here, we seem to still be talking about health as a general thing for the whole application. Is it possible that an application can have multiple states of health? Because in an architecture a bit like this one, spoiled my next slide, in an architecture a bit like this one, different parts of that architecture could go offline and things might be okay. It's Schrodinger's infrastructure. This is the cat in a box with poison, and at some point that hammer is going to close and release the poison. And you can't see inside the box. Of course, within our infrastructure we can, and we can monitor this. But the idea is, in Schrodinger's cat, the cat is neither alive nor dead because you don't know if it's alive or not dead. And I would compare your application health to this too. Your application can be both healthy and unhealthy at the same time because parts of it can fail and other parts can keep running. So take this architecture again. If we take our inventory service out of the mix here, in an e-commerce scenario, we have a front end. All monitoring would say, yep, users can go to our Amazon.com, they can browse our products, they can see the catalog, they can add them to their cart and proceed through the checkout, and they can even take a payment. But because the inventory failed, we have no way of validating that we actually have that item in stock, and we have no way of notifying the warehouse that you need to put one of these on the side and actually ship it to a customer. But that feels like a recoverable problem, something that doesn't affect day-to-day users. It will affect your business operations, but you could deem that Amazon.com is operating correctly without that inventory service being in place. Similarly, if we look at the payments side, not being able to take a payment for an Amazon.com of the world would be a catastrophic failure. They need to be able to process payments. But if the email service goes offline and they can't send the confirmation email to the customer, you could argue that's a degradation of service. It's not ideal. But it's not a catastrophic failure. You're still able to take payments, you're still able to process orders, customers won't see any different. What we're going to talk about today is ways that you can build architectures like this that have that baked-in resilience, give the option to resend those emails later, or retroactively go and fix your inventory service when it comes back online. I'm going to come back to this CrowdStrike issue. So I mentioned earlier, we work with some fairly large hospitality organizations, let's say, and we run loyalty schemes for some of their products. Those loyalty schemes, as you can imagine, are a bit of a mess behind the scenes. We're talking, the airlines and the hotel chains of the world that have 20, 30 years of customer data there with historical activity of that customer, how many flights has this person taken, how many times has this person stayed with us. They have a CRM type system backing it. They'll have APIs for that CRM system that integrate through various other third parties. So you may not be talking direct to the CRM, you might be talking to an intermediary. You have the ability to log in to your favorite airline or your favorite hotel's website and see all of that activity. And that might pull in other things too, because you can sometimes connect two loyalty schemes together. In the case of Qantas, for example, you can connect your everyday rewards and your Qantas, and those two systems can live side by side within one account. But what if one of those goes down? And we learn this the hard way, because one of our big high-profile customers, their primary CRM API went offline. And that meant that the homepage of their website, beautiful, you can see all of their products, their offerings. You can click on the login button, and then you just get a request that hangs forever. And the issue is we're doing a single sign-on there, where we're passing off to another application. It's not our application that's offline in that case. It's just that no users can get to our application in the first place. And then we started to think, well, how can we recover? We're talking with the supplier. What's your expected recovery time on your service when you're going to have this fixed? Oh, we don't know. We're completely in the dark. It ended up being 2 days. And that meant that we had a system that was non-functional for the best part of 2 days for something that was out of our hands. But the reality is it's not. It is in our hands. We can control that. We need to start baking in the relevant mechanisms to make that possible. So let's talk through a few scenarios. Calling an API in its most basic form is probably the most obvious way that someone's application might fail. Whether it's a REST API or calling off to a service that you have running internally, it doesn't really matter. The same idea applies. You're calling something external, and that thing might not be there or might not respond the way you're expecting. So if we look in this scenario here, we've got a request, it's calling an API for API/results, and there's effectively two different things that can happen. We can get a response saying, OK, and we proceed. Fantastic, all's good. Or we might get a 500 server error, for example. Something's gone wrong, probably on their side, not something we can do. Now, to bake some resilience in, the most basic thing you could do is just try again, do another retry. Sometimes these APIs are rate limited, sometimes they've got temporary blips. Sometimes if you're dealing with a smaller platform, you might catch them in the middle of a deployment or some maintenance window, and that's okay, so do a retry. From a programming perspective, this is quite an easy thing to implement. If you imagine a try-catch type block or pattern that you'd use in JavaScript or Java or C#, you would do your initial call. If it fails, in your catch, you go try to do it again. Some mistakes can happen here, though. We see people who bake in a retry mechanism, probably they've built their own, and then they just retry indefinitely or for a very long period of time. And you end up DOSing yourself, your own application. You effectively create an infinite loop, your own performance issue, just because some other third-party system's offline. That's not ideal. People also, I see very often, handling success or failure as being a binary thing with calls to APIs. That's certainly not true, because there's a reason we have a full spectrum of status codes. They tell you information about what's happening with the service. 200 OK, great. You can assume if it's in the 200 range that we're able to proceed. A 500 range means, yep, something's gone wrong. But if people are handling just worked, didn't work, you don't handle the cases like it failed because our API token has expired, or because some other reason. Maybe maybe it's a DNS level failure and not just a server response. How do you handle all of those different scenarios? Well, it's more important to bake into your retry logic some conditions that say we're going to retry and we're going to retry this many times and for this long to make that retry actually reliable. There's a technique called backoff. And so what you can do is you can build into your retry mechanism a retry with an n+1 delay. So you say, okay, I'd like you to retry, but I'd like you to retry in 5 seconds, not right now. Just wait for a bit and then retry again. This works great if you're building an asynchronous system, less great if you've got a user that's waiting for a response. Decide what's appropriate. But this backoff idea is that it will keep going until it reaches a certain threshold. You can say, I want you to retry in 5 seconds, and if it fails again, okay, retry in 10, retry in 20, retry in a minute, up to 10 times or something. This is where circuit breakers come in. Circuit breakers as a technique is a way of having that retry and that delay, but also having a cutoff where we say, no, stop, we've reached a threshold. So in our scenario here, we get an error. If it's all gone through successfully, that's fantastic. But if it fails, it will then start a timer that says, okay, you need to retry in this amount of time. And if it fails repeatedly, you can then have your application set a flag somewhere that puts a message up to the user that says, this area of our application is unavailable for now. You can have handlers that say, oh, this task has failed repeatedly. We're going to let you know somehow internally in internal metrics through telemetry that someone needs to go and look at this. Maybe you don't care about knowing that once every day one of the API calls fails, but you do want to know if it's repeatedly failing, so you can go do something about it. So this circuit breaker pattern is a really nice way of building some of that tolerance into your system, where you don't infinitely call an API, and you make the user experience much nicer around what you know about that system. And the circuit breaker can be almost self-healing as well. You can say every minute, I'd like you to go and just retry one more time. But you're not then backing up loads of calls to their platform and creating a negative experience for your users. This all sounds really complex, but I promised a JavaScript example. Node.js has a great library called Opossum that does exactly this. It's circuit breakers, and that's all it does. Not for APIs, but for any function in actuality. So in this case, I've got Opossum. I've loaded it in. I have a function called getData that does something. Let's say it calls an API. And then within my circuit breaker, rather than calling getData directly, I use the circuit breaker to say, I'd like you to call that getData function until you get a response that we're satisfied with. In this case, we're saying when 50% of the total number of requests to that endpoint fail, consider the circuit broken. Stop making requests here. And then you can see in this case it says log the response or log the error. The timeout here says try again within 30 seconds. So you're going to see 50% of the threshold get hit, and then, okay, we now need to wait 30 seconds before we send any more traffic to that. The circuit breaker pattern essentially handles all of that for you. Within these catch functions, you can then do your own logic to say what you want to do, be it turn off that feature for users, be it send a Slack message to our team to say, hey, this thing's happened, or put something in telemetry. In the .NET world, we've got a far more comprehensive library called Poly, which is really excellent. By a quick cheer or show of hands, .NET developers in here? Good. We're amongst friends. That's great. Poly is lovely. And when I was looking at some JavaScript examples for this talk, I found lots of different Node.js libraries that do all of these different patterns, circuit breakers, retries, but there's no single library that does it all. And Poly is that library for .NET. It's fantastic. So Poly is essentially a resilience library for .NET. And it, again, much like Possum, it's not specific to API calls. It's just specific to a function gets called, and it runs, and it passes, it fails. Do we want to keep retrying and calling this? I've got a code space up and running that we can actually have a look at this in practice. Oh, and maybe first, a little honorary shout out. Microsoft does have a very basic version of this called HTTP resilience, which is designed to wrap around the HTTP client, .NET's effective API client that lets you call external endpoints, and you can then bake in your own little retries and reattempts exactly through this. So it's purely through like a configuration syntax. You can start to say, I want you to retry after this. It's a good thing to go look at. But more importantly, Poly is this full-featured library that does kind of everything. They follow a strategy pattern, and so in the strategy pattern, you can define a set of criteria, a set of things that should happen when a function fails or succeeds. So in this case, you build up a resilience pipeline is their core concept. And within that, you can insert strategies. So in my case, I'm adding a retry strategy. And within the retry, you can say this is the maximum number of times you should retry. This is the behavior that you need to do. Do you need to back off exponentially or just one time? What delay should we have before we go and retry and do the same operation again? Jitter is a fantastic term in resilience, but jitter essentially allows you to add a level of like fuzziness into the metrics. It's a bizarre thing, but if you were one trying to emulate something, jitter's really helpful. Or two, if you just want to make sure that you sort of fail safe, you're on the more eager side of failing, actually having a bit of jitter within your telemetry is a good idea. And then the handling, they've got this sort of handler pattern for deciding how you then handle certain types of response. But all in all, this is a generic wrapper around running a task in .NET. So pipeline execute async, you pass in your task, and then it runs. Within this, you can decide, as I said, to turn things on and off, how you behave this, if you service this to the user or not. Depending on if you're making a user-facing action that needs this retry logic would probably determine what you end up doing. You might have a message that comes back to the user after 10 seconds saying, sorry, service is unavailable, try again later. If it's a back-end service, it's more likely that you'll want to have internal telemetry that says, this thing happened, someone's got to go fix it or find out why or recover. Let's talk about the critical paths in our applications, because that's also equally important. The critical path would be exactly what a user engages with, and making sure that's as smooth as possible is critical. In the case of our e-commerce example, I love using e-commerce as an example because there's so much that goes on behind the scenes of processing your simple add to cart pay on Amazon, and this is vastly simplified even still. But if you imagine a very basic e-commerce implementation like this. You have a cart, and you add items to your cart. You then have a step that runs between adding items to the cart and displaying the checkout, which is check if we have these items in stock. And so you'd have your inventory service that goes away, and it runs and it checks. And then on the checkout, the user enters their payment details, and then we go to the next step, which would be capturing those payment details. Finally, we send an order confirmation to say, yep, all good, we've received your money, and then we display them a page that says, success confirmed. We've received your order. But what happens if email fails at this point? So we've taken the cart, we've had a user add an item to the cart, we've checked the inventory, is all good, we've collected their details, we've even collected their payment, but then they just receive an error page on the website. They never receive an email to say, thank you, we got your order, and they never receive a screen to say, all good, they just get an error. And they only find out 7 days later, when the bank has still actually taken the money from their card, that the order went through. You've got to hope, maybe, somewhere in this process, the e-commerce site goes, yeah, I understand, something's gone wrong, maybe reaches out to the customer, actually process the order, but you don't know. That's horrible. So what we need to do is try and make sure our critical path is as error-free as possible, so that an end user doesn't encounter these types of scenarios. What we need to do for that is move to a more, event-driven type approach, where certain events can happen in conjunction with a user behavior. So when you add an item to the cart, the inventory in the background can then go and reserve the items. That can happen on a background thread, and if it fails, it doesn't matter to the user. Similarly, when you perform your checkout and you want to verify or capture your payment, again, that can happen on a background thread. You can send them to their success page before your payment has actually been taken. If anyone uses Amazon, you'll notice that there's about a 30-minute window after the point you hit pay before they go and collect the payment. And similarly, your order confirmation, it might come through within 30 seconds, but sometimes it takes 20 minutes. That's essentially what they're doing here. They are processing that payment offline. They capture all of the important details they need to go and fulfill the order, and then they trigger a whole chain of things to happen in the background. So in this case, our cart was successful, checkout was successful, and we captured the payment, but if the email confirmation fails, it's not the end of the world. The user still sees a success page. They still have an order number at the end of the day. This is still fairly flawed, though, because actually we need a system that can proceed in cases only when a previous step or some background tasks have succeeded. And that's where having some kind of queuing system actually makes sense. So exact same flow here. Our goal is to go from a cart to a checkout where we collect their payment details to a success page. You'll notice here that rather than having an order success page, we've actually got an order pending page. This is also what Amazon will do. The wording may not be quite like that, but essentially they're saying, yep, all good, we've received your order, not we've taken your payment, not it will be here on this day. Anything that they are saying there is merely an indication of what might happen once all of their background events have finished. So in this case, we have a cart that rather than performing the action it needs, it actually performs a validation step. So when you add an item to the cart, we'll do a very light cursory check over the inventory service to see, is this item in stock? If it is, all good, you're ready to proceed to the next step. Having that there is critical because you don't want a user trying to buy an item that isn't in stock. That's a fairly typical business practice you wouldn't want. Same on checkout. You want to verify that their payment is available, but you maybe don't need to capture the payment there and then and have it all confirmed by the bank. You can always confirm or not confirm the order later, depending on the result of further checks. And then you take them to a pending page. So those little verification checks, what they would do is go, yes, all good, I can do that, and then put a task onto a queue somewhere and have another process, a subscriber in this case, go and capture those events that fire. And when those events fire, an individual service could go and process inventory. So back to our big sort of microservice architecture we showed at the start, your individual inventory service, rather than being spoken to directly, reads off a queue. It waits for instructions. A queue is just a list of instructions that are not associated with any individual service. And multiple subscribers can then listen to the same events as well. You can have your inventory service trigger a warehousing task, make it trigger the reservation, all sorts of things there. So similarly, capturing payment happens offline, sending the email happens offline. The benefit of having a queue in this system is that if at any point one of these systems fails, let's say the email service is down, we can't send emails today, the queue still has the list of tasks it needs to perform. So we can go and replay those items, reattempt to send those emails at a later date. We're not directly reliant on the email service being available. Benefits are we can take it down for maintenance and all that other kinds of things too. Let's talk a bit about failover, because failover is another really important strategy here. Sometimes in infrastructure, things go wrong and we have to be able to turn stuff off. Having a kill switch was one of the things that we actually put in place for our service. We need the ability to turn off sections of our system at the drop of a hat. Maybe it's a maintenance window, maybe it's actually the upstream provider's having an issue. But we need the ability to just temporarily turn off those features manually. There's a manual failover option. But you can also do this with your own infrastructure. So let's take our infrastructure here as an example. We've got a very basic application, a database, and some storage. And we can have a primary and a secondary infrastructure. Using a tool like Azure Front Door or Application Gateway, you can create these health checks. And these health checks are responsible for detecting of multiple versions of your infrastructure which are healthy and then appropriately routing traffic. So in this case, the gateway performs a health check. It calls the ping endpoint, gets a response back, 200 OK, and says, yep, all good. That region is available within our pool. In the case where it gets a bad response, it then takes it out of the pool. Much like our retry logic that we had a moment ago, these can happen repeatedly. They can be called on at certain intervals. You can determine how often and how many times these requests need to fail before you determine that this pool is unhealthy, take it out. If you're really risk averse, then you'll say one failed health check or one health check that took slightly too long to respond, take the entire replica out. Or you would say, no, actually it can be a bit slow. It's within our threshold. We'll still allow that to operate, but it might then trigger a task for an engineer to go and have a look at and see why is that infrastructure running slow. There are some challenges with this replica type approach though, and replicas require replication. If you've got data in an application, you need somehow a primary source for that data. This is where queues are really handy because you can have a central queue and eventually have all of the data in all of the places when all of the systems pick it up off the queue. That's called eventual consistency. But it's a hard thing to achieve. So people stick with this kind of traditional A, B, blue, green, primary, secondary setup in their infrastructure in a typical disaster recovery platform. The reality is this is not a reliable mechanism for a lot of big organizations. This is a concept I hadn't heard of until 2 years ago, and it might have been invented by this company I'm about to talk about. In the UK, we have a bank called Monzo, and they've invented a bank, effectively as a tech company. They've built the entire infrastructure from scratch. It's all Kubernetes and fancy. They've created, it's like one of the most popular banks in the UK, top 5 most popular banks in the UK at this point. They've created a stand-in platform. And this is to handle a few things. One is infrastructure failure, or infrastructure provider failure. They host on AWS primarily. And they said, we need to host on GCP as well. I don't know why they didn't choose Azure. I love Azure. We want to host on GCP as well. And you run that question then of, okay, do we go for full replication? We just have a copy of our infrastructure running on GCP all the time, and we've got to keep our data in sync somehow. Or you take the approach they've done, which is they have a miniature version of their architecture that runs on GCP, that in an absolute crisis they can fail over to at any moment in time. So of their around 3,000 microservices that run on their primary AWS platform, they have distilled their business logic down to 18 core services with minimal behavior living in this stand-in platform. And they have both an automated and a manual trip switch that decides whether they route their traffic to one or the other. So they've got some kind of gateway that's sitting in front of this. This is really cool because it means that they can take their bank offline for maintenance, but card transactions can still be processed because it just goes to the stand-in. And they've determined that, yeah, card processing is critical, but we don't care that checks, do people still use checks? Checks can't be processed then, or that you can't send $10 to your mate because you can just do it later. But your card transaction when you're paying for groceries, that has to go through. I really like this approach. Wouldn't work for every organization, and most of us aren't running systems with 3,000 services in them. But distilling your behavior down to a simple set of functionality and having a very basic version of that deployed is really cool. How do they keep their data in sync between these? Again, it's a queue. They have a queue system that sits centrally, and that writes to their primary ledger that lives in their primary platform, but they also write to their stand-in platform simultaneously. So every single action that happens, both platforms look at the same queue, or the same cluster of queues, to determine whether they then need to update their relevant bits on their side. Replication happens continuously. They don't have so much of a concern about eventual consistency because they're not thinking about it in that way. They're just more services that they're running. So yeah, interesting approach. Okay, some of the challenges that come with running all of these sorts of approaches. We've talked a lot about moving towards event-driven things, using queues, changes the way you architect your platform. Means that you have to think more that processing does not happen immediately. You have to bake into your user experience that actually this thing could take a little bit of time. And then monitoring this is really tough. I have a longer version of this talk where I go into some examples of how you do monitoring and tracing with things like OpenTelemetry. And in the .NET platform, we've got .NET Aspire now, which kind of glues all of that stuff together and makes it really quite easy to do, which is nice, exciting. There are some amazing data telemetry platforms out there and application monitoring platforms out there. The obvious Azure Application Insights, but also Honeycomb, Datadog, and New Relic have all got fantastic tools in there for working with open telemetry standards for receiving information and then surfacing that in a nice way. So you, as an engineer, have a friendly dashboard that shows, yes, our 95th percentile response time is this, and you can trigger a whole chain of events that alert when certain things are falling within those thresholds. If you're not using one of these already, you should. Of an application of any size, it really makes working a lot easier, and especially at scale. Testing is another really interesting angle, because it's all well and good putting these architectures in place, and it will feel completely futile until you need it. But the moment you need it is when it really has to work. When a third-party provider you're integrating with goes down, like, how do you test that? Well, Netflix created a thing called Chaos Monkey about 10 years ago now. And this is essentially their microservice system. They needed a way of validating that, if we take this service offline, what happens? And also to sort of keep engineers thinking about that failure state, those failure modes in all scenarios. We should be able to handle this service going offline, or if we can't, we need to handle that gracefully for the user. So Chaos Monkey, they've got a fantastic open source library there that effectively does this in an infrastructure level to take services offline. But it doesn't work if you're not using microservices. Azure have a service called Azure Chaos Studio, which is essentially this, but productized, and they will take individual routes and bits of infrastructure offline for you within those simulated scenarios. So it's a great way that you can bake this into your testing processes. When you do your performance testing, when you do your unit testing and your behavioral tests through your application, also test that it's able to withstand these failures. And finally, because I love Poly, and I said at the start, Poly has chaos simulation baked in, and they have these really nice, quite friendly endpoints, friendly extensions that you can call on your service to add a chaos fault. And the magic number you're seeing on the left-hand side here is essentially the percentage of requests that they should apply to, the percentage of actions they should apply to. So we can say, for 10% of users, throw this exception, give them an error, see what happens. You can have random latency added to certain calls that go through the Poly Poly pipeline. You can randomly determine the outcome being different to what your service actually responded. And you can even create your own custom behaviors here, like we're going to take Redis offline, or we're going to do something else there. So it's really pluggable and quite friendly and configurable, which I think is really cool. And I am 1 minute left. I hoped I'd have some time for questions, but there's a break. I'll be around. There is a Poly example on my GitHub that shows it in a little bit more widespread use. I'm on all the social medias at those same handles. I'd love to hear your experience of doing things like this too. I know people in this room work with platforms of different scales and sizes, and will have their own unique challenges and unique ways of handling that. So let's chat. But thank you for your time, and thank you to the sponsors for this amazing event.